Alright, hello everybody. I am Charlie Tin, and I am going to, do the video about matrices and linear transformations. Now here is just the general layout that I wrote beforehand, so that we could have like a big picture of where we're going. So I kind of like browsed the notes a little bit, and I decided, these are kind of the important stuff that we want to gain out of EE16A. So I'm just going to go and read this outline right here. So first I wrote down, I don't know how clear this is, but we're going to start with the linear transformations actually, because I feel like that's a good place to start visualizing, and I like to approach things from a visual perspective. So it's basically like with geometry, like kind of what a transformation is, and eventually we're going to have to explicitly represent this mathematically, and how do you do that is matrices. So then I'm going to talk about matrices after that. So contrary to expectation, I'm going to do linear transformation and then matrices. So I'm going to do some properties and some special matrices. I'll talk about them a little bit, and then there is going to be describing how to do matrix multiplication, and also I'm going to give some examples because this whole class is an engineering class. It is about I don't know if you can see it. It is about applications. So I'm going to talk about some geometric applications of linear transformations, and then the page rank algorithm. All right. So I'm just gonna. I hope this is clear. If this is not clear, you can just email me, or just ask the professors to alert me or something like that, and I'll make a new one. Alright, so let's just get started with just general concepts, right? So we have in our minds an idea of a function, which is, let's talk about real valued functions. Okay, and then there is, basically we put in a number and we get out a number, and this is what we're used to in math, and we just do this a lot. Now I'm going to introduce a new type of function. It does not take a number and it does not return a number. Rather, it takes in a vector and returns another vector. So let's first talk about some general function concepts. So there is domain. And then there is codomain. And there's range. So let's go over some of these definitions. The domain is just what can it take in such that this is it works. It can actually be put into this function. So in this case, it's all reals, and that's the notation we're going to be using. It just means x is a real number, and then this codomain is also all reals. It's a real valued function. But that just means, codomain means you look at it, look at the type of function, and it'll tell you a certain thing. So this is all reals because we're expecting a real, and we're putting in a real. But the actual range is all positives. Okay, so that's why we kind of like to discern between codomain and range. It'll be kind of more clear why we do this when we approach a new type of function. In this case, it's a linear transformation. So let's talk about some output vector called E. Is some transformation on A. So what this really means is just kind of, we're going to put in a vector A to this function, and we're going to output a vector B. And here's just some standard mathematical notation for, what it can take in is a vector. And it outputs a vector. That's what makes it special. And this vector we call a part of Rn, which just means it's a selection of data. And this is what we're concerned about in electrical engineering and other engineering fields, right? Data. We want to take numerical measurements and put it concisely. So in applications, this will typically be n sets of data. And then the codomain is Rm, meaning it will output a vector that exists in Rm, which means it has m sets of data. All right, and then the range we'll get to later. But just a little preview, it's equal to call A if this is being multiplied by matrix A. We'll explain later. And now you can see why I determine a difference between codomain and range. Range is kind of what can it do, and it's not necessarily everything in RM, but sometimes we just want to see how much data am I getting back. And if you only care about how much data you're getting back, you're only going to care about it's part of RM. All right, so hopefully this was clear. And now I'm going to introduce a visual representation, just in case this wasn't. But this is a real value function, right? Takes in some input and returns an output right there. Well, it's a bit harder to draw for vectors, but it's a very similar concept. So let's say we took some random vector in R2. We're just going to see our R2 since I can draw it on this blackboard. And now we apply some transformation to it. V. And then it goes here, where I rotate it by theta degrees. And for sake of simplicity, I'll just do R2 to R2 since I can just draw on this blackboard. Now, that's an example of linear transformation as well. I can do anything, well, not just linear, it's just a transformation on a vector. I can do anything to this vector, some series of mathematical things. We're just going to abstract away here, right? That's the power of abstraction. And then we're going to return another vector. I hope this was a clear visual representation of why we like to, do transformations. So, and here's some other common ones. We're going to do it later in the geometry example. Reflection across the y-axis. And then there's also, for example, rotation that I just did, or reflection across the origin from here to here. So this is V, this is T. Right? So yeah, this is some geometry, and this helps you think about transformations, not just like, I'm just multiplying this matrix and plugging in number by number, but it can also be used to represent stuff in real life. Like in that midterm, you have the robot arm rotating. This can represent this too. So that's very nice. But now that we have attained this visual representation, let's kind of like, it's more helpful now to be able to explicitly calculate what vector it's going to return. So we're just going to introduce some new concepts. Right? So let's just give an example of a vector, not visually, but just like purely numerically, not in mathematics terms. So it's just a set of data, really. It's like an array in Java, or a NumPy array, right? We're used to NumPy. So then this takes in, say n is 2 here. So let's say I do 1, 2, right? It's part of R2 because it has 2 reals. And as a result, it's just basically, it stores in data. Let's say we measure like the x position at some times, and then we get these, just some random example. And that's data, and that's what we're going to use in engineering. And now let's, transform it. Let's say we wanted to see what's going to happen to it if we apply some transformation in the next time step. I'm being very vague here, but let's just go through the math, like the hard math first. And we're going to see that, we're just going to introduce a new mathematical concept called a matrix. And I'll show you soon why a matrix is actually considered to be, if you multiply it, a linear transformation. So a matrix is really just, you can think of it as a collection of column vectors or rows. For this purpose, I'm just going to consider it a collection of column vectors. So it's basically just filled in with data. Again, dimension data. So then you start with like your first row, first column entry, and then you go to your m, and then say n rows and then n columns, so mn. And this would thus be 2-1. That's how the numbering system works. And then that's just basically a collection of data, and it fills it in, and it tells you, it's just, we're going to see some examples later. And then we can, we can do some things. Let's just first introduce, addition. If I add it to another one, B, first of all, we have to make sure it's the same dimension. Yeah. And what that outputs is really just what you would expect. You add the corresponding terms, and then those are what goes into your matrix. So everyone can see this, right? I'll just give a quick example. So let's say I had 2, 3, -1, 2, plus -2, 3, 0, 4. First of all, let's check that they can be added. This is 2 by 2. This is also 2 by 2. And we're going to get 0, because 2 minus 2 is 0. 3 plus 3 is 6. -1 plus 0 is -1. And 2 plus 4 is 6. So we get this matrix. Simple enough. So let's just, go through some properties. This might be useful in some proofs that we've seen, on the first midterm with some, just calculation simplifications. So because every term in the resultant is determined just by addition of reals, and for addition of reals we have commutativity, we have associativity, we can apply the same thing to addition of matrices. So A and B are matrices, so A plus B is equal to B plus A. This is just commutativity, and then we have, associativity. Right? And then we also have special matrices. We're going to have the zero matrix, which is just a matrix full of zeros. Every single entry is 0, right? Or not a vector, just 0. So A plus 0, the additive identity. And also if we took something we call the additive inverse, we would get 0 as a result by adding it. That's the definition. And how we get this is by transforming each term in A to the negative. And then we add it to each other, and every single term in the resultant would be 0. And then similarly, we have scalar multiplication, which is also as intuitive as one might expect. So we have, C times A11 to AMN, and we are going to get CA11 to CAMN. Essentially, that negative thing was a scalar multiplication of -1 to the whole thing, and here we're just going to use any scalar. And it's intuitive, right? You just go through every single element in the matrix and you multiply it by this scalar, right? So let's just show another example. Let's make it quick. So 3 times 2, 1, -1, 2 is going to give you 6, 3, -3, 6. Right? Because I'm just multiplying 3 of every entry. Output it. Right, so that's just, matrices. Now let me introduce something. In the previous not lectures, just like these, helpful videos that other EE16A students like myself have created. Well, they have taught you a perspective of matrix multiplication that I will not, I don't want to waste your time over it. But you have columns, and then you multiply it by a vector in Rn, or a whole matrix, right? But if it's a whole matrix, you can just think of that as a collection of vectors in Rn. And basically, this one is multiplying this first column, and this one is multiplying this second column, and it's so on and so forth, like a linear combination of the two. And then we're going to do this column by column and get a resultant. Well, let me tell you something that's equivalent, right? And you can see some rigorous mathematical proof. I will not go over this because, like, if you kind of intuitively see that, you know, the first column, first value, gets from, you know, the first values of each of these columns times this. So you can see kind of a linear combination of these column entries with the linear combination of the first of these column entries, which is just the first row, right? So these go down like that, and then you have one first row. And then these linearly combine. So what do we call that kind of linear combination? We call it the dot product. And now we have a new definition of matrix multiplication. So if A is n by n, and B is n by p, notice that these two must be the same in order to multiply. Then C over AB equals C is n by p, and C's element in row I, column J, is equal to the dot product of row I of A dot col J of B, right? And it is exactly what I said. The first element of the resultant is the first row dot product the column of this. So yeah, you can generalize that and prove it if you're interested in math. It's already almost 20 minutes, so I will truncate that. And the reason why these have to be, this means there's n elements in the first row, and this means there's n elements in the columns. Now to do a dot product, both of the vectors have to have the same dimensions. So let me pick up the pace a little bit and just show you a special matrix, and then I'll show you why it's a linear transformation. Right? So, you know, let's do some examples. Right? And then, what's the first element? Well, you column, row, you do it. 3 plus 0 is 3. Column, row. That's 2. So that's 2 plus 0 is 2. Row, column, 0, negative 1. And then row, column, 0, 0. So what does this equal? Wow, this is the same as this. And that's no coincidence, because this is a special matrix. This is an identity matrix, right? And then I'll subface it n. Is n by n, and it has ones along the diagonal and zeros everywhere else. So there, you have ones along this diagonal and zeros everywhere else. And that's, you know, I2, because it's 2 by 2. All right? So, and the proof for that is you can just kind of do some, the column definition of matrix multiplication. You're going to see that you're multiplying this by the first column, and then you're adding it to this by the second column. And this first column, or in here, is only going to preserve the first item. So your end up first item is preserved, right? 3 times 1 is 3. And then the same for the second one. It's going to preserve the second item, and it gets multiplied by this second entry, and then you can go down the chain, and you'll see that it is preserved. But that is for, you know, mathematical proof. We're interested in properties now. So I'll, you know, it's just to gain some intuition. I'm pretty sure there are some linear algebra texts out there that will give you a proof. Also, I think the 16A notes also give you a proof. I just kind of explained it very quickly why the identity matrix works the way it is. But after reading about linear transformations, we can see more clearly how it behaves. So why do we call this linear? Well, let's define what it means to be linear. All right. So let's take two vectors, A and B. Well, if this is a linear transformation, this transformation T, then what we should get is by definition. All right. Second property, all right, is we have some constant, scalar constant C times some vector A, and you can just pull that out. And this is what it means to be linear. Constants don't matter, right? You can think about it as like a line, and then you can just pull out that constant, the slope, and it's still a line. So let's see why this is linear, why multiplication is linear. Well, it can be clear because it is clear why it is linear because well, let's take some matrix, right, and then it has columns A1, AN, and then we multiply it. On some vector x, and then we're gonna, just take the linear combination of these, and then we can see that if I had another vector like b, that this, when you add vectors, they add linearly. That's a property of vectors, because you can also think of vectors as matrices. Well, these add up, and you're still multiplying that. So now you can do it through everyone, and you're going to see that if you transform this by matrix multiplication, you're going to get what you get if you transform this and then added this, because you're going to get, as your first column, well, actually, not as your first column, but as your first contribution to the column. But you can expand it to the other contributions, it'll still be linear. And then you can, distribute x1, b1, and then that's the first property. And then the second property is the same thing, right? If I multiply this by like 3 and everything here by 3, and multiply this whole vector by 3, and then that gets distributed here into the columns. So we have thus concluded that every single matrix multiplication is a linear transformation. Okay, sorry for taking so long, but I just kind of want to show this concept because this concept is very key, because linear transformations are very common, If it's not linear, you can always approximate it such that is linear. And then we can now find some explicit way to kind of just say, how do we make this linear transformation happen? And that is where we got this, and that's why I think this is very special. Now, but can every linear transformation be represented as a matrix multiplication? So now here's where we get to the interesting stuff. All right. So let's take an example first. Okay. So in this example, we are going to have some input vector. Remember, all transformations can be also expressed geometrically since it's a vector going to a vector. So in this case, let's take some vector, and rotate it, right? Same rotation by theta. Now, how are you going to do this? It just seems so hard. How do I just multiply some matrix to any vector and it will rotate by theta? This seems all very, abstract. Well, let's use some properties of linearity to help us get there. Okay, so we're going to do what we call standard basis. Okay, and what this means simply is that, well, okay, let's work out an example where this not only rotates here, but it's going to make every transformation, makes some dent in this dimension. We're going to say this is 1. Actually, let's make this better. This is, I just want to, right, so it transforms here and it also makes an upward appearance. And that's height 1, okay? So now how are we going to do this? Like, you're not even staying on the same plane, so you're going from R2 to R3, and now you're expecting us to, just magically be able to find this matrix that represents the transformation. It's very complex. So what we're going to do actually is, first of all, think about the dimensions of this matrix, and second of all, I'll show a concrete algorithm for getting your resultant. Okay. So yeah, this is going to be 3 by 2. That's the first step. We have to know the dimensions. And why is it 3 by 2? Well, think about what happens when you multiply this, right? I already said that m by n matrix multiplied by n by p matrix, and in this case, m by p, n is 2 and p is 1, right? x1, x2. So, and p is 1 is going to result in an m by p1. So we want something m by p, and what is m by p? We're going to R3, so m is 3, and p is still 1, so that's good. So m is 3, that's the important part. And we know this is 2 because in order for matrix multiplication to work, if this is 2, this must be 2. And this is 3 because we wanted a result in R3. So, but how do we fill it in? Guess and check? Well, that's not very effective. For very, trial and error is not going to be very efficient. It's not going to give you any insight. Let's do the analysis of the linear property. So if this vector x, we're going to call this E1, we're going to call this E2, standard basis. And why? Well, it's because they're easy. They only have one component. They're axes, right? This only has x, and this only has y. Everything else has a combination of both. So this is a combination of both, right? And since it's a it's a combination of both, well, we can just use some linear properties, right? So T and this is the direct result of the fact that this is a linear combination. Matrix multiplication is a linear transformation. So if you're going to retain the same, like structure essentially of the vector, this standard basis vector gets transformed to something, this standard basis vector gets transformed to something, and this is going to take the linear combination of both of them, which is what happens when you multiply this and this. So in this case, A1 is just X1, right? So let me just change this to A1 and A2 for consistency. All right, and then we're going to use the property of matrix multiplication. That is just, this is multiplying by the first column, this is multiplying by the second column. So this is the same thing, right? It's multiplying by the first column, this is multiplying by the second column. And now we can see that this first column is what you get by transforming this one, and this second column is what you get by transforming that one. And now we have developed a method that can quickly, because these are the easiest vectors, right? They only have 1 and zeros. And you only have to do 2 of them, calculate the transformation of 2 vectors that determine transformation of any vectors. I find this very powerful, right? Because it's just, it's just linear combinations and transformations can allow you to basically tell this vector to go anywhere, and you can know exactly how to define this. It's pretty hard even in real numbers to just tell this real number to necessarily go, anywhere. It's like if you describe it only with a visual representation, not an explicit formula. Well, if with a vector, it's easier, right? So let's take what happens to E1 when we rotate it by theta and put it 1. So let's just think about it. Well, it rotates by theta. So its x is cosine theta now, and its y is sine theta, and its z is going to be 1. For the rotation of the second one, we're just going to do some angle addition formulas and add theta to each of them. So cosine theta plus 90 is going to equal to sine theta. And then sine theta plus negative sine theta, excuse me. And then sine theta plus 90 is going to give me cosine theta, right? And then, and this comes from the fact that it's equal to 2 cosine squared. Not 2 cosine squared, but it's going to be equal to, let's just write that down for anyone who wants to follow along. In this case, 2 is just 90, so this becomes 0, and this becomes 1, so it's negative sine. And then this is also just 1. So now we're done. We can construct from geometry this matrix. So this matrix of transformation, I'm going to call A. That's geometry. Now I'm going to go really quick over an algorithm called PageRank algorithm. It's very similar to the float palms, and in fact, I think that's why I was introduced to this. I'll just, start off with some assumptions and then tell you about how it's transforming vectors. Okay, so real quick, I'm going to introduce this one. So Google and stuff want to know which one of website B, website C gets clicked on the most, so it finds the highest probability that some random server is clicking around on some pages is going to, it's going to eventually stop somewhere, or at some time t, this like random server, where you're going to be. So the sum of probabilities, it can either be only A, B, or C. In real life, obviously, it's a much greater example, which for A, B, and C, you can theoretically calculate the probability using mathematical formulas. But for like in real life, there's more than 3 websites that exist, right? So Google wants to find out which website is going to give you, the highest probability. Like, what is the highest probability that I am on website A, for example? All right. So they're going to have to use some mathematical modeling that doesn't involve direct theoretical computation. And this is how we're going to do it. Well, let's say that there is at some time there is a 65% chance, say at A. There is a 40% chance, say at C, and a 20% chance to say at B. And then from A to B, it's going to be 0.1. And from A to B, it's going to be 0.1. And then from C to B, it's going to be 0.2. And from C to A, it's going to be 0.25, so on and so forth. I'm just going to go ahead and tell you that if you want to model this situation, that we're going to use a matrix that represents going from column to row. So A, B, C, A, B, C. So from A to A is 0.65. From A to B is 0.1. From A to C is 0.1. From C to C is 0.4. From B to B is 0.2. I haven't said B to A, I'll just say right now it's like 0.4 and 0.25. And C to A is 0.25. Is this it's ugly. So this is 0.4, 0.2, that's 0. Okay, so notice that here the columns don't add up to 1. And this is because it's a damping factor. What this means is that if you're there, there's an 85% chance that you'll even stay on this system of 3 websites, or you're just going to log off, do some work. So that's why it's 0.85, because there's a 15% chance at each time step that someone somewhere in this location is going to log off. And basically, we multiply it by some state. So we're just going A, B, C. This is how many people are at A, B, and C. And this effectively captures what happens if you go one more time interval. And what they do here is mathematically, iteratively, multiply this by this over and over again. And we have a way to do that. If this is square, they call this A. And then we want to do n times A to the n. So that's how powers work in matrices. It's just multiplying by itself over again. And that's the PageRank algorithm. It's similar to a flow problem, except we must take care to assume that the internet, no one's going to stay on the internet forever, and we must take care to assume this property. So thank you for your time, and I hope this review has been helpful. If this is too long or if this is unclear to see, please email me, and I will promptly make another one.